I'm very happy to welcome all of you. My name is Markus Eberle and I will moderate through this webinar today. So this is the last session of today, but we still have 2 more days with a lot of other topics we can speak about. But today our topic is operating voltage of molded power inductors, and I'm also happy to introduce Jens Kehl, our speaker today. Hi Jens.
Hi Markus.
So yeah, Jens will do the presentation today for you, and also he will answer your questions. Those will be at the end. So we will first go through the presentation, and then we have time scheduled for your questions. If we can't answer all your questions within this live webinar now, we can answer them later on also via email. So just feel free and contact us. Yeah, so that's enough from my side at the beginning. I wish you an exciting webinar, and Jens, yeah, have fun.
Thank you, Markus. Thanks for the introduction. So hello everybody, my name is Jens Kehl. I'm a product manager for the power magnetics team in the Würth Elektronik. I'm today here to present to you a research topic that we have done in the past few years, which is for the operating voltage for molded power inductors. So this is the agenda of today's webinar. First, I want to give a detailed introduction to this topic. First, I want to show some market trends that we are seeing, which will also show why the operating voltage definition is needed for molded power inductors, and also how it might differ from other products that we have, from our other inductors like ferrite-based inductors. This is also why I want to show you the molded inductor production process, and also deep dive a little bit into the materials that we are using for this. And then I want to show you some phenomenons about these molded power inductors. Afterwards, we will see some effects that is caused by too high voltages in applications, and what are the effects that we will see there. At the last point, I want to show you how we have defined the operating voltage for the molded power inductors. I want to get into detail what is the detection method, and then also how transparently we are showing this into our data sheets, but also within an application note. So I will start now with the introduction. First, I want to talk about the market trends. The first trend that we are seeing is that we have much more design-ins coming for molded power inductors. So maybe you are familiar with these products that we see here on the slide. So for example, we have the PD2 series, which is a ferrite-based inductor, and we see more and more coming that we get requests for molded power inductors like our MAPI series, but also like our XHMI series. They have a lot of benefits. For example, you can see 4 of them here on the slide. So they have a very compact design, very high power density. They are very stable over temperature, and they offer soft saturation, which is good for high current spikes. Then another trend that we are seeing is a switch to higher switching frequencies. So this is coming because there are new developments in FET and also in HEMT technologies. And we are also seeing that lower inductance values are required for these new FET and HEMTs. And also the power inductors can be much more compact. Then for the next topic, the input voltages. So we are seeing also an increase in input voltages for some applications. We are actually having a poll here for you. For this, I would like to have Markus back here.
Yeah, of course. So now I just shared the polling with you. So now you should see it on the right-hand side. It opened and we already can see the first answers there. So I'm interested, or hopefully, I think you can also see the outcome here. I think the first option, we are going there.
Okay.
Yeah, really interesting.
Looks very interesting.
more and more will come. Yeah, very cool. Okay. So what does that say to you, Jens?
Yeah, it's very interesting. So we see that now it's coming more and more that's actually quite equally distributed, right?
Yeah,
so
yeah.
We see in the lower voltage range, there's the majority of answers. So this is also what we are seeing from our customers at the moment. Yeah, but we also see the trend a little bit that higher and higher voltages are also required. Yeah, so this is very good to see.
Okay.
Thank you.
Thank you for joining or for taking part at our poll. So yeah, thank you.
Yeah, thanks, Markus. Okay, that was very good, very helpful. Thank you. And then, yeah, so we're seeing also over 120 volts is getting more and more interesting. Also for the molded power inductors, of course, yes. Then the last point that we are seeing is also a switch in the duty cycles that are used. So I have here an example because previously there were a lot of FETs that weren't, that had a very low efficiency. So it wasn't possible to, for example, switch 48 volts directly to 1.8 volts. So it had to be taken in steps. So for example, it would have been needed to switch or to change 48 volts into 12 volts, then to 5 volts, and then at the end to 1.8 volts. But since we are getting more and more devices that are very high efficient, we can now directly switch from 48 volts down to 1.8 volts. And this even at an efficiency of greater than 90%. And this, of course, has a big influence also on the inductors that are used in the application. Then next up, I want to talk more about the production processes. There's a big difference in the production process between discrete components, so the ferrite inductors, and these molded inductors here. So here you can see a very simplified 4 of the production processes that we are taking for the molded power inductors. So very basic, we start with a wound copper wire. This is of course the basis of our inductance that we want to have. Then we will have a material mixture that is containing mostly iron powder, but also a binder material, which is basically acting like a glue to get this then pressed together in the next production step. So we fill the wire into a mold and then the material mixture completely around it in the mold, and then we press it together with a very high pressure. This of course means that our wire is completely filled and completely covered with the core material itself. Then to get the binder out of this mixture, we cure the parts in an oven. So this will mostly remove most of the binder material. Now I want to talk a little bit more about the material that is actually used. So first of all, I said that this is mostly containing iron powder. So here on this picture on the right hand side, you see how these iron particles actually look like. But of course we know iron is conductive, so this wouldn't be a very good core material actually. So all of these iron particles that you see there are actually coated. So you see this here in this picture. This coating is very important for our inductive behavior that we want to have. But also this will have some influences on the voltage that we can apply to the parts. So this coating layer can be actually made thinner or thicker. But this of course will also change then the inductive behavior of our core material. So there has to be a balance in how thick the coating will be. And then of course we are also adding the binder. So here in the last picture, you see how everything is then looking together after it has been pressed and also cured. So you see that this is really sticking together all of these iron powder particles. So we have tested a lot to find out what is actually the operating voltage of our components that we are currently offering, and also what we will bring out in the future. And we have seen that especially this binder material and this the mixture then with the iron powder can cause some issues here. So we can see that there's actually something like a short circuit happening directly over the core material. And this is something that we want to prevent, because this is kind of like a material degradation, we call it. We will see this later in the next few slides. So I said this is a material degradation. Of course, then the next question is, how can we detect this material degradation? Here it gets a little bit tricky, because if we take a look into standard qualification testing, also like ACQ testing, which we are also doing for all of our industry parts, we are mostly testing inductance value and RDC. Here I've taken a picture from an LCR meter with a good part. So the good part is directly coming out of the reel. Now I have also a compromised part here. Compromised means we have pushed some high voltage spikes onto the component to get this material degradation happening. But you can see here from the inductance value and also from the RDC, nothing really changes. So the part is still good. So what are we doing now? Of course, we have done much more testing, and we have actually found that the Q, so the quality factor, is the main driver of this phenomenon. And this is also something I want to show you now in more detail. So I have here a graph. This is showing Q over frequency. The first graph shows, it's called here after soldering, but actually this is before test. So actually we test the parts directly out of the reel for the Q value. Then we solder the parts and check the Q again, just to make sure that the soldering process didn't change any of the Q behavior. And then, so this is a good part. We have done all of our procedure that I will come to later for the operating voltage definition. And we see before the test and after the test, everything is still fine. So both are matching. So there's no degradation in the material. Now we can take a look at a bad example. So here we have purposely destroyed a part, I would say. This is also completely different inductance value. That's why also the Q value here looks completely different. But here again, this is after soldering, so before the test. And now we can see here how the Q graph looks after the test. We already see this is a big difference. So there are two things happening here. We see that the peak is actually shifting to lower frequencies. So if this peak would be this peak, actually, this is shifted to a lower frequency. But also, of course, the value is dropping a lot. So this is actually increasing our losses quite dramatically in the inductor. And especially at high frequencies, this change is very dramatic. So if we take a look here, maybe at 1 megahertz, which is a typical switching frequency, the Q value change is very dramatic. Now we want to take a look what this will have as effects in our applications. Especially taking a look for the dropped Q value. We have here an example application. This is a buck converter with an input voltage of 18 volts, output voltage 5 volts, switching at 510 kilohertz with an output current of 1 amp. We have used this board here on the right hand side, and here this small board on top. This is actually where we can interchange our inductors that we want to test. So we have tested two parts, basically. One part directly fresh from the production, and then one compromised part. So here you see also what I mean by compromised. So we have put multiple voltage pulses over 200 volts over a part. So during our testing, actually, we found that especially the ripple current is very affected by this. So this is something I want to talk about now. I want to take one step back to a little bit basics about the buck converter. So on the left-hand side, you see the simplified buck converter in the schematic. And on the right-hand side, you see the ripple current that we expect from this application. So what we found is that this short circuit I've talked about before in the core material itself will add some parasitics behavior that we didn't have before. And this is mostly a resistive behavior. So this you can see here in this slide. The inductor now has kind of like a parallel resistance, but this parallel resistance is getting much bigger than it usually is. And this also has a drastic effect on the ripple current, which we can see here on the right-hand side. So first of all, we have like inductive behavior, like we expected, but then suddenly the ripple current drops to resistive behavior. And then it goes back up to inductive behavior. And this actually adds a lot of losses in our inductor that we didn't or that we don't want to have. So these losses, of course, they have a very, very big impact, especially on the part temperature. So this is something I want to show you now. On the left-hand side, you see the good part. On the right-hand side, you see the compromised part, so the kind of destroyed part with a lower Q. We see here the temperature reading for the good part, which is running just above 40 degrees Celsius. And now I have another poll question for you. What do you think the compromised part has now for a temperature?
I just heard poll, so I'm back again. Hi.
Hi, Marcus.
So yeah, we see the first of you already taking part at our poll. And oh yeah, we have a clear meaning. Yeah, it's so the first answer. No, not so many wants to take part there.
It's good. No. It's good that the first answer is not getting too many.
Okay.
Okay. So the majority is between 41 degrees Celsius and 80 degrees Celsius. But also a lot of people have guessed over 81 degrees Celsius. That's very good. Yeah, so between 22 and 40. Yeah, so if we see that the part is a good part is already above 40 degrees C, now we have higher losses. So of course we expect also a higher temperature of the part.
Makes sense for me.
That's great. Okay, but now I want to also show the actual result. So the part now actually has a temperature of 118 degrees. So that is much, much higher compared to before. This is almost 3 times as high.
Crazy. Okay. I didn't expect that. Yeah,
we also didn't, but we found this.
Okay.
Very interesting.
Cool. So then, thank you.
Yep. Thank you,
Interesting poll.
Yeah, so we see that the losses increase is very, very dramatic, which also causes this temperature rise. Okay, now I want to explain to you how we are defining the operating voltage. Actually, for us, this is an additional test because there is no test standard that is available from IEC or equivalent. So we had to come up with our own measurement and test procedure that we want to have. Actually, there are some test procedures, detection methods available, also used by our competitors. We have also tested this because mostly this is done with just some short voltage pulses that is then detecting the response from the device under test. But for the molded inductors, we have found that this is not really useful, especially for low inductance values. So that's why we have partnered with one of our partners from Belgium. They're called Mindset. I think you should be also able to receive a link to their website right now. So you can check them out because we have custom developed measurement equipment together with them to fit our needs. Because our goal was that we can test our power inductors very close to the end application use. But this is actually a very different approach to any of our competitors. But with the results that we are seeing, we are very confident that this is the right way to define the operating voltage for the molded power inductors. Also, the goal was that we can also change, have the very variable settings. So for switching frequency, but also for duty cycle, and that the very high voltages are possible. So how is this machine working? This is actually a full bridge DC to DC converter, which you can see here on the left-hand side. And in many cases, this is very close to the end application. With this device, we can test up to 1000 volts. So this gives us a lot of headroom also for the future to test. And as I mentioned, we can change the switching frequency and also the duty cycle at which we are testing. So on the right-hand side, you see the voltage waveform out of the machine and also the current waveform. So one thing I want to emphasize here is that we are always talking about operating voltage. So this is basically the mean voltage that you are expecting in your application. So it's always possible that there are always some voltage peaks that you are expecting. This is just coming from the end application, of course. So we are defining the operating voltage in our testing, which means actually we are testing at a higher operating voltage, and then we are adding a safety margin so that it is safe for you to use also with these voltage spikes. Actually, we are testing here not, as I mentioned, how our competitors are doing with short pulses. This is with continuous switching. So we are continuously switching over several minutes the device under test in this application until we get a measurement completed. And we haven't stopped there. We actually also are doing full 8-hour runs with our inductors under test to also check for long-term effects. And next I want to show you what we are doing with all of these results. So we have done a lot of testing in the past 1.5 years, and we are now ready to promote the operating voltage in our datasheets. So now you should be also getting a link to this MAPI size 4020 datasheet. So we have here the electrical properties, and we are expanding these with one more column. So you see here everything that is usually there. Inductance value, performance rated current, which my colleague Alexander Lang just did a presentation on. And then we are also adding this operating voltage here. Then also because we want to be very, very transparent, we have also written an application note, which is called ANP 126. And this application note is actually available on our website since last week. And you should also just receive the link to this. So if you want to get more details about this topic, please just check it out. And if you have then further questions, you can reach out anytime. So we have actually defined the operating voltage for 3 of our product series at the moment, which is most of our molded power inductors portfolio. So we have defined it for the MAPI series, which has an operating voltage of 80 volts for all of the sizes. And we have also defined it for the LHMI and XHMI, which will have an operating voltage of 120 volts for also all of the sizes. And then this actually concludes my presentation. So I hope it was an interesting topic for you. And then we can jump into the Q&A.
So, Jens, thank you very much for your interesting presentation. I liked it very, and hopefully you did as well. And yeah, let's jump in right into the question. But before we do that, I will quickly share the handout with you so you can just download the slides you just saw. I see some of you are already clicking and downloading it, so you should be able to see it right now. And now we still have some time left for your questions. So Jens, then we start with the first one. What is the difference between the operating voltage of a non-molded inductor compared to a molded inductor?
Okay. Yeah, so maybe this question comes because our non-molded inductors, the ferrite inductors, they have the operating voltage stated in the data sheets for quite a long time. But yeah, I've showed especially the production process of the molded inductors, which is completely different to a ferrite inductor. So ferrite is typically sintered at very high temperatures. So there's no binder material left inside of the core material. And for the molded inductors, this is not possible because the wire also has a different temperature grade. So there will be still some residue of the binder in the material, in the inductor itself. So that's why we have seen in our testing that because of this production process, actually the operating voltage has to be completely defined.
Okay. Jens, thank you very much for the answer. Then we are finished with this one, but we have here the next question. Will there be also molded inductors capable of more than 120 volts?
Okay, yeah. So we have seen in the poll also, right, that this was also requested. So currently we are stating 120 volts. This is basically coming from also the market demand that we have seen or mostly getting from our customers. But of course, we are also working on getting inductors out that have also higher voltage rating. So currently we are stating 120 volts, but for sure for the future, we will also work on higher voltage inductors.
Thank you, Jens. So good news for you, Marie. Then I hope you can live good with that answer. So then we can just hop on to the next question. Why is the operating voltage not only defined by the wire insulation or wire grade?
Okay. Yeah, I mean, this can be assumed because actually the wire grade typically for voltage is very, very high. So I think the lowest wire grade has actually a breakdown voltage of about over 2000 volts. So it could be very near that you could also apply over 2000 volts over an inductor, right? Because the current is just flowing through the wire. But yeah, we have seen through the testing, also with the ferrite inductors, that there are also a lot of parasitics playing a very big role here. So it's not just the wire itself that is needed for an operating voltage definition, it's the whole system also with the core material.
Okay, thank you very much. Then let's go on with this one. Where can I find the power inductors products from Würth Elektronik? Probably on our website.
Of course, the website, in our online catalog, of course. But I always recommend also to check out our Red Expert online tool, because there you have very good filtering options, but also different options for checking out some simulation tools for DC-DC converters, for example. And you have also filtering options for the operating voltage there in place as well.
Okay. Thank you very much, Jens. Then last question I see for now, and probably I can also answer this one. Will the recording be available on YouTube? Yeah, you can already see the first recordings of our digital V-Days on YouTube, and we will just get them online in the next few days. So, and you also get the link from us also to the handout. So if you missed something, then just contact us, and we also will share the link with you. So then I think we are already finished with our session. And yeah, thank you very much, Jens. Thank you for your time, for the presentation and all the answers.
Thanks.
And yeah, then just stay tuned. I wish you a good evening, and yeah, hopefully we will see us tomorrow. Thank you and goodbye.